Imagine standing on the edge of a quiet field in Colombia on a bright March afternoon. The air is ordinary. Birds, a distant tractor, the smell of turned soil. And then the sky does something no one expects. A perfect metallic ball, small enough to cradle but large enough to be strange, drifts and jerks through the air with movements that make pilots and balloonists wince. It doesn't glide like anything we know. It darts, it zigzags, and then, with a sudden, incomprehensible stop, it plunges into the ground and is gone from the sky. People run toward the impact site thinking they'll find a machine, a fragment, something explainable. Instead, they find a whole, seamless orb. Scientists arrive. Journalists arrive. The world leans in because when something this odd lands on Earth, our assumptions about the possible begin to tremble. Now, overlay that scene with something else, something colder and faster than rumor. In the months since that field in Buga first saw the metal ball, a second story has been spinning across the internet. It whispers that Grok 4, the newest AI from Elon Musk's XAI, a system built to browse and reason with live data, ran a digital twin of the object and warned of an impending internal failure. Think of that for a moment. An AI that reads the web in real time, draws on the latest papers, news, and measurements, then spins a virtual copy of the orb to test what might happen next. Grok 4 exists, and it does include web-connected, tool-using capabilities that let it pull in fresh information as it reasons. That means it can, in principle, run simulations based on live data in ways older AIs could not. But here's the vital, uncomfortable truth. The claim that Grok 4 predicted a catastrophic breach is not the same as proof that it did. The most reliable reporting we can find documents the object, often called the Buga sphere, and it reports the mysterious physical findings that sparked alarm. A seamless shell, strange internal structures visible on scans, weight readings that changed over time, and localized damage to soil and life where the object landed. News outlets have covered the discovery and the strange measurements. They have not, however, produced a verified transcript or screenshot of Grok 4 announcing a breach. What exists in the public record for now is a swirl of original observations about the sphere and separate online posts claiming an AI model analyzed it and predicted failure. Those are two different things. Treat one as documented fact, and the other, the AI prediction, as an unverified high-stakes rumor for now. So why does that rumor hit like thunder? Because the physical details of the sphere, the ones we can point to in lab notes and news articles, are themselves extraordinary. Labs that examined the object reported behavior that reads like a fiction writer's checklist for impossible stuff. The orb felt cold to the touch. It exhibited a net cooling effect on nearby material instead of the expected warming. Scans revealed multiple nested layers and tiny metallic spheres inside. And instruments at the crash site recorded molecular-level damage in soil where nothing radioactive could be detected. Those findings, if confirmed, are a problem because they don't fit comfortably into the physics we use to build things, to compute failure modes, or to keep satellites flying. They are the kind of anomalies that make engineers sit up and say, if true, our models are missing something big. That's where an AI's warning would matter. Space agencies and aerospace engineers already use machine learning systems to spot trouble before it becomes disaster. NASA has run programs and prototypes showing that AI can spot failing thermal systems or predict hardware faults earlier than manual checks alone, giving operators precious time to act. When an AI flags a satellite's heat behavior as abnormal, engineers listen. Extrapolate that capacity to an unknown machine that seems to be bending heat and mass in ways we don't understand. And suddenly, the hypothetical prediction of overheating takes on a real and alarming weight. If an advanced model with current web access built a digital twin and found an unstable thermal balance inside the sphere, that would be a red flag the size of a flare. To make this feel even more immediate, picture how fragile quantum systems are. In labs around the world, researchers work to keep qubits, the fragile building blocks of quantum machines, at temperatures barely above absolute zero. That requires massive, elaborate refrigerators and constant power. The largest dilution refrigerators under construction, take up rooms and demand continuous energy to hold those near-impossible cold spots steady. In short, maintaining extreme cold at a small scale is hard engineering. It's not something that happens by accident. So when reports say a basketball-sized object is holding temperatures that could plausibly house quantum processes with no visible power source or cooling equipment, it becomes not just mysterious, but potentially dangerous. Those who study quantum devices know that if thermal balance is lost suddenly, stored energy can dump catastrophically. Mechanical ruptures, rapid expansions, electromagnetic phenomena, the kind of rapid, violent failure engineers dread. And then there's human nature. When something scary and unknown appears, our first instinct is to tell a story that makes sense of it. We look for patterns in the past. Odd orbs and strange artifacts have long haunted human imagination, from reported rolling spheres in the 1970s to mythic tales of glowing balls of power in ancient lore. Those echoes make the Buga sphere story stick. They make people prone to connect the dots, sometimes responsibly, sometimes not. The responsible path is the cautious one. Confirm measurements, publish methods, invite outside labs, and verify claims. The irresponsible path is to take an unverified simulation, dress it in certainty, and spin fear into prophecy. We also need to separate failures of measurement from failures of the device. Lab work is messy. Instruments have calibration errors, contamination, and unexpected cross-effects. Soil that looks sterilized in one instrument might be explained by sampling technique or chemical contamination. Weight that seems to increase could come from moisture uptake, adsorbed gases, or changes in measurement conditions. That's why independent verification matters, and why scientists quoted in coverage urged caution. Several experts suggested the object be submitted to broader, independent analysis and compared against known materials and manufacturing techniques before leaping to exotic conclusions. The news coverage reflects this split. Vivid claims about the object's oddities and steady voices calling for rigorous cross-checks. Now imagine how information flows when national security and big science collide with an object like this. If what's inside were a genuine, functioning quantum core, or a device exploiting unfamiliar physics, it would be both a scientific treasure and a strategic prize. That creates real incentives for secrecy, for fast, guarded analysis, and for competing interests to act quietly. It also creates incentives for misinformation. People and groups might exaggerate what they know to gain leverage, funding, or attention. That mixture, real mystery plus high stakes, is a perfect pressure cooker for rumor to become panic if left unchecked. So what should happen next, and what would sensible people actually do? Step 1 is transparency in the method. Laboratories publishing raw data, instrument configurations, and independent replication attempts. Step 2 is inviting specialists who are not emotionally invested in the object's origin, materials scientists, cryogenics experts, isotope analysts, and independent instrumentation labs. Step 3 is measured risk assessment. If there is any credible evidence that a core depends on a fragile thermal balance, protocols for safe handling, remote testing, and containment must be activated. The same way hazardous material teams respond to unknown chemical agents. None of those steps are dramatic. They are slow, careful, and boring, and exactly what keeps the world safe. Many experts quoted in coverage urge this cautious approach rather than performance and spectacle. And about Grok 4, XAI has publicly released information showing the model's capabilities have evolved. Newer iterations can interact with live tools and fetch up-to-date information in real time. That capability makes the idea of a web-connected simulation plausible. But plausible is not proof. Public model cards and technical notes tell us what the technology can do in broad terms. They don't provide evidence that a particular run of a model produced a particular catastrophic prediction. The responsible path for journalists and scientists is the same as for lab technicians. Demand the raw output, the logs, the simulation parameters, and the chain of custody for any claim that could justify red alerts around the globe. There's a moment where science becomes human, where instruments line up and the quiet facts start to carve a narrative you can't ignore. Consider the recorded mass changes that made physicists do a double take, readings that increased over weeks while the object sat motionless. If that's confirmed under repeatable, calibrated conditions, it's not just odd, it's a fracture in assumptions we've used to build modern physics labs. Mass conservation is a bedrock principle. Challenging it would shake the foundations of many fields. Yet, extraordinary claims demand extraordinary evidence. That's the rule that keeps science honest. If you want to change physics, bring the data with ironclad controls and independent replication. Nothing else will settle the question. If replication confirms the anomaly, we face two paths. One is careful study, replication, open methods, and slow, methodical probing. The other is competitive secrecy, labs and agencies pulling the object into private facilities, cutting off outside review, and racing to extract advantage. The first path gives us credibility and safety. The second gives us speed at the cost of certainty, and possibly at the cost of safety itself. History shows both outcomes are possible. Remember the Manhattan Project. Secrecy produced a terrible, world-shaping power. Secrecy can also protect sensitive research from sabotage or theft. The trade-offs are real, heavy, and messy. Whatever the true origin of this sphere, whoever controls its study will be making choices with global consequences. We also need to reckon with the role of AI in this story. Advanced models like Grok 4 can pull new reports, papers, and lab notes together and propose simulations. They can surface connections faster than any single human team. That's an enormous advantage for scientists, and an enormous responsibility. If an AI simulation flags a high-risk scenario, it doesn't mean the world must panic. It means humans must pay attention, evaluate the model's inputs and assumptions, and act accordingly. AI can amplify both our wisdom and our mistakes. The difference lies in governance. Who vets the simulation? Who verifies the inputs? Who stands behind the conclusions? Right now, the public conversation features an unverified social feed claiming that Grok 4 predicted a breach. That claim should be probed like any other scientific hypothesis. Ask for the inputs, the code, the logs. If those aren't available, treat the output as a lead, not a verdict. Let's look at the stakes in stark terms. Suppose for a moment the worst plausible engineering scenario plays out. A thermal collapse, rapid energy release, and an electromagnetic disturbance. Satellites could be affected. Communications could falter temporarily. Sensitive electronics could reboot or fail. That's the realistic end of many engineering analogies. It's not necessarily the apocalypse, it's instead a sharp, disruptive event that would make daily life harder for a time. Governments and operators plan for such events, for solar storms, for EMP scenarios, for radiation bursts, because similar effects are within their hazard models. So one practical upside is this. If the failure modes people are warning about are plausible, they also fall into categories that engineers and resilience planners already handle in part. That makes mitigation more tractable than many fear narratives imply. Here's the final, human point. Curiosity is a double-edged sword. It brought us out of caves and into labs. It also brought weapons and risks. The Buga sphere story is a test of how well contemporary science balances urgency with caution, transparency with security, and awe with responsibility. We can choose to respond like a frightened crowd, amplifying rumors and leaping to conclusions. Or we can respond like a community of practice, document, verify, and communicate clearly. An AI highlighting a risk should be a call to audit and confirm, not a reason to weaponize worry. So what should you take away sitting at home or pacing in a lab? First, the sphere is real enough to have drawn serious scientific attention. Mainstream news outlets reported on its recovery and on initial analyses.